There we go. We are recording. Okay, before we tackle lesson 1, I just want to remind you where the unit circle comes from. Can you guys kind of roll ahead in the booklet here? We'll go past lesson 1. And I think, where are we going? Hang on, I'm going to shrink this. That way I can go through it faster. There's the unit circle, but where does there we go. Can everybody go to page, on mine it's 18. I hope yours is the same booklet as mine. Can everybody go to page 18 really quick? Right, is that yours? Page 18 looks like this? Okay, good. So what's special about the 45-degree right triangle? Well, it's actually the only right triangle you could have that is both a right triangle and it's isosceles. It has two sides the same. Right, think about it. Really, at the end of the day, it's like you took a square and you cut it in half, diagonally. Right? So that's what's special about the 45-45 triangle. So we, if you remember back to grade 11, put that on the unit circle. We put that 45-degree triangle in a bunch of places. But actually, before we do that, let's assume that this hypotenuse here is 1. How long are its sides? Anybody remember that from grade 11? Is it a half? Oh, there we go. Somebody's got a radical happening. Yeah. Why? Well, think about it this way. What else do you know about right triangles that you learned in grade 8? You learned Pythagoras' theorem, right? And you learned that, a squared plus b squared equals c squared. And in this case, if it's isosceles, a and b are the same. Why don't I just call it x, make my life easier. So x squared plus x squared is 2x squared. 1 squared is just 1. X squared is equal to 1/2. And if x squared is equal to 1/2, then x must be equal to plus or minus the square root of 1/2. Now, back when you were in grade 8, jumping from this step here to this step here, you didn't bother with the whole plus or minus. You do understand why it has to be there, right? Just to think about it with an easier number. X squared equals 9. Right? This is a piece of algebra. Some number times itself is 9. Well, that could be 3 or -3, right? Because both of those numbers times themselves make 9. So why didn't we talk about that in grade 8? Well, because in grade 8, we were only worried about Pythagoras. We were worried about the length of a line in a triangle. And it probably didn't make that much sense to start telling grade 8ers about the possibility that a line can be a negative length in a triangle. But now in grade 11, of course, you realized, well, actually, it's quite important that we think about it that way. So first of all, let's simplify this up. Square root of 1 is just 1. And the square root of 2, you also learn in grade 11 that we don't usually, in mathematics, like radicals in denominators. So do you remember what we did with that? We multiplied it by root 2 over root 2. And then we have ourselves now the final answer of 1 times root 2. And root 2 times root 2 is 2. And that's the number some of you remembered. Isn't it root 2 over 2? Yes, it is root 2 over 2. It's 1 divided by root 2. These numbers are the same, right? I didn't change. Remember, when you multiply something by 1, you don't change what it is, right? So there we go. That's what's special about it. So if you now go to, say, one of your practice unit circles that I gave you, oh, and yours looks a little different than this, but it's still basically the same thing. Yours has dots, mine has lines. That's this guy right here, right? This is 45 degrees right here. And this line here let's use fancy colors. I'm going to erase that. I'm going to use blue for my 45s. So this spot right here is 45 degrees, right? And this blue line here and this blue line here are both the square root of 2 units long if the hypotenuse is 1. So let's just assume that the radius of this circle is always 1, right? So what else do I know about this distance here that's going along this line, and what else do I know about this distance here? They also happen to be the x and y coordinates, right? If this is the point 0, 0 in the middle, this right here would be the point 1, 0, and this right here would be the point 0, 1, and this would be negative 1, 0, and this would be 0, negative 1, and over here, this would be root 2 over 2, root 2 over 2. Now, why do we care about any of this? Who cares what these coordinates are? Because they also happen to be the sine and cosine values of 45 degrees. Because if you now look at this as an angle, if you now look at this as a right triangle, and this is an angle, well, the cosine of the angle is the adjacent over the hypotenuse. And the hypotenuse here is 1. So it's the x coordinate. So all of the points going around the unit circle are cosine of theta, sine of theta. And then, of course, we learned in grade 11 that we can also put that over here. We could put the same triangle, but you just pick it up and flip it over and put it over here. I was supposed to be trying to trace that line. I didn't do a very good job of that. There we go. Of course, I can't really call this spot here 45 degrees because we start measuring here and we measure all the way around like that. So how many degrees is that one? Who remembers it? 135, very good. So this is 135 degrees. And it almost has the same coordinates, just a little bit different. What's different about them? The x is negative because I'm on the left side of the axis. Which is why, if you take your calculator, can I make this bigger maybe so I can draw bigger? There we go. Which is why if you take your calculator and you type in what's the cosine of 135 degrees, it will spit out negative root 2 over 2. In decimal form, it's 0.707, blah, 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 blah. And that's what you learned back in grade 11. And again, this is now very, very important. Why is this important? Because we do not, starting in grade 11, and certainly again here in grade 12, we do not limit trigonometry to right triangles. In fact, we don't need triangles at all. We can just talk about angles. The next place that this happens is down here. So add another 45, you get 180. Add another 45, you get 225 degrees. And it's the same coordinates again, only now x and y are both negatives. And if you add another 45 degrees, you get down here to the 270 mark. But then add another 45 degrees, and you hit 315 degrees. And now x is positive again, but y is negative. So if you ask your calculator what's the cosine of 315, you'll get positive 0.707. But if you ask it for the sine of 315, it's going to be negative. You even kind of memorize that maybe as a rule. The cast rule, because cosines are always negative in this quadrant. And speaking of this quadrant, how do you number quadrants again? This is quadrant 1, this is quadrant 2, this is quadrant 3, and this is quadrant 4. Remember that? All right, let's go back to page 17. Or no, what was it again? 18, right? Let's go back to page 18. We've just dealt with the 45s. What about the other one? There we go. The 30, 60, 90 triangle, where does that come from? Well, imagine an equilateral triangle, which means that, of course, all the lengths are the same. And I'm going to call them all ones. And imagine that I took scissors and I cut it perfectly in half. Now I've got that triangle that has, once again, a hypotenuse of 1. But now this baseline here is 1/2. And then what would this line be? Well, once again, let's call it x and use Pythagoras. A squared plus b squared equals c squared. A squared plus that equals that. X squared is equal to 1 minus a quarter. X squared is equal to 3/4. So x is equal to plus or minus root 3 over 2. So let's, now, this was, of course, an equilateral triangle I started with, which means that it had 60 degrees up here, it had 60 degrees up there, but when I cut this in half, this is now 30 degrees. So this is the 30-degree angle, and this is the 60-degree angle, right? All right, let's put all the 60-degree angles down first. So go back to your unit circle, and let's see if we can make that happen. So let's see, where are we? Unit circle. There we go. So the 60-degree angles are the big guys. So they go here. So I'll use a different color. I'll use red for the 60-degree angles. So my 60-degree angle, so the triangle that I just drew, or that I just labeled, I should say, is right here. So that's my 60-degree angle. Let's label it up there, 60 degrees. What are the x and y coordinates this time? Well, we just figured out that the x coordinate, this is 1/2, and this is root 3 over 2. Because that's how tall this line was. We just found it. Now I could put that triangle over here instead, and this would be 60, 120 degrees. And my x coordinate becomes negative, but my y coordinate, I'm trying to make that a negative. There we go. But my y coordinate stays the same. Then down, add 60 again, and I get to here. Add 60 again, and I get to here. Okay, so that was 60, 120, 180. So this guy here is 240 degrees. He has the same coordinates, only this time x and y are negative. Add another 60, you get to here, which we call 300 degrees. This time x is positive again, but y stays negative. Exactly. So, quick, what's the sine of 240 degrees? Don't all shout it at once. Yeah, right here. Right? Sine's the y value. Okay, so that's what the unit circle is for. Now, we're not quite done yet. There's still some points because, go back. I said go back. There we go. This triangle here could be rotated. Let's see, am I using black right now? No, I'm still in the highlighter. This triangle here I could rotate this way so that the 30 degrees is there, the 60 degrees is up here, and then the proportions are still the same. If that's a 1, that's a 1/2, and this is my root 3 over 2. So what if I put that triangle all the way around the unit circle? Okay, let's go back to our unit circle. There we go, unit circle. So let's see. So it's really, I should stick to red because it's the same triangle. I'm just flipping it over. But here, I'll use a different color. I guess I'll use green this time. Green. There we go. So my green triangle goes here, where the 30-degree angle is that way. It's still the same as the red triangle. I've just flipped it over. So it's 30 degrees. Whoops, I didn't mean for a bracket on that. So it's 30 degrees here. And it's the same two coordinates as the red guy, just flipped over, because now the x is the longer side and the y is the shorter side. Okay, if that's 30 degrees, what's this guy? Hint, another 30 gets me to 180. Right, that's 150. So this is x is negative and y is still positive. And this guy here is 180 plus another 30, so 210 degrees. And that's x and y are both negative. And this guy, if you added another 30 degrees, you'd get to 360, so he's 330. And x is positive, but y is negative. And that is your unit circle. We expect that coming out of grade 11, you could do what I just did without touching a calculator. So if I ask you, just again, calculator free, quick, what's the cosine of 210 degrees? You should be able to make this sketch and find it. So if there's people who can't do that, go to that lovely grade 11 review that I gave you, where there's a bunch of questions like that, and work through it so that you make sure that you've got the grade 11 skills. Because we're not slowing down to reteach them. We're expecting that that's kind of what you already know how to do from grade 11 trig. Okay, now I got good news for you. You don't need it just yet. The first lesson in grade 12 isn't really so much the unit circle. So let's scroll back to the first page here. There we go. Whoops, didn't mean to do that. There we go. The first actual outcome is right here. Demonstrate an understanding of angles in standard position. But now we're going to express angles in not just degrees, but in radians. I'll bet this happened to you in grade 10. How many times was your answers wrong because you accidentally hit that stupid button on your calculator that took you out of degrees? Oh, that was frustrating, wasn't it? Well, now we're actually going to talk about measuring angles in something called radians. First of all, starting here at 4.1, what do we mean by standard position? An angle is in standard position if it has its center at the origin and its initial arm along the positive x-axis. Let's draw that. What we mean by that is, first of all, again, this is quadrant 1, this is quadrant 2, this is quadrant 3, this is quadrant 4. Yes, it's traditional to use Roman numerals. No, I wouldn't mark you wrong if you didn't. So if I have an angle, let me use blue here. If I have an angle, this blue line here is going to be its initial arm, because like it says, the initial arm is along the positive x-axis. And yeah, you put a little arrow at the end of it. And then an angle is really the distance between two arms. So the terminal arm, I'll make that one red here. The terminal arm is this guy. And of course, the distance between them is our angle. We'll call it theta. That's kind of the go-to variable for angles. Now, there are positive and negative angles. Positive angles go counterclockwise. This is where everybody looks up at the room's wall and sees a digital clock. I have met students who told me they'd never seen a non-digital clock. They'd never seen a clock with a face and arms that go around until they moved to Canada. Because there are countries that just don't look at face clocks very often. Okay, well, you're just going to have to remember then, starting here, this is leftward, right? And of course, this way is clockwise. This is the way an actual clock goes directionally, like that, okay? And these are my negative angles. So for example, this angle here, let's put an estimate on that. Oh, I don't know. Theta here looks like it's about, well, let's see. From here to here is 180. That's 270, so I don't know, 255 degrees. That's just a guess. I don't know. Slap a protractor on it and measure it if you want. What's the terminal arm on this one? Well, the terminal arm on this one's going that way. So now let's see. Let's see if you could get me an estimate for this. If I went from here to here, I'd have negative 90. That'd be negative 180. That'd be negative 270. So maybe that's about the same. Theta here is about negative 255 degrees. All right. If that logic makes sense to you, if you've never thought of angles as being positive or negative before, they are. It's a directional thing. Let's try a couple here. Which quadrant is 400 degrees in? So let's think about that. Let's make a little sketch. If I'm going positive, I'm going this way. Ooh, there's 360. So it'd be further, but it certainly wouldn't be another 90. It'd only be another 40, right? So what quadrant am I in there? 1. Okay, I'll give you a minute. You try their other 3. See if you can guess which quadrants they're in. That's a guess. It's not a guess. Make yourself a little sketch. I'll never forget one of the times I was doing this very page, and somebody was trying, they did see next, and they said, 5! Quadrant 5? I guess they figured because you keep going around, you're just going to keep numbering. No. Oh, actually, I guess it was A. That's right, it was A. They thought it was quadrant 5 because it went around. They went 1, 2, 3, 4, 5. They thought A was in quadrant 5. No, I'm afraid it's still quadrant 1, even though we're hitting it the second time around. All right, give people a minute. Oh, I see people with their pencils down already. Good. Was that easy? I'm glad. All right, where's 65 degrees? Let's make a sketch. Oh, negative 65. Okay, if I'm negative, I'm going that way, and I'm not going to make it to negative 90. So I'm in here. 1, 2, 3, 4. Did you get that was quadrant 4? 700. Okay, get ready. Ready? There's 360. 360 plus another 180 is, well, wait a minute. 360 doubled is 720. So it's almost all the way around again. What quadrant am I in now? I'm in quadrant 4 again. And all right, where's negative 150? Well, if I go all the way to here or so, if I keep going, I'd hit negative 180. So I think I'm in there. So that's 1, 2, 3. All right. You know, the provincial exam almost always had one question like this in the multiple choice for 1 mark. Just what quadrant are you in for an angle? That's like the easiest mark on the whole exam. So there you go. Now, I think the next page is an activity, isn't it? I'm going to skip this activity. You know what? You can do this activity yourself if you want to. What you're going to learn from this activity is what a radian is. And basically, a radian is a way to measure an angle that doesn't involve just saying, well, the distance as I sweep all the way around is 360 degrees. That's a completely arbitrary number, by the way. They could have said it's 100 degrees. Why didn't they pick 100? You know, think about the metric system. We base everything on tens and hundreds. Why 360? Well, 360 is a more useful number if you have to break into factors, right? 100 only has factors 1, 2, 5, 10, 20, 25, 50. You're out of factors. Think about how many factors 360 has. 1, 2, 3, 4, 5, and 6 are all factors. You don't have a 7, but you have an 8, a 9, a 10, a 12, a 15. I think does 16 go? I think 16 goes. 18 would go for sure. 20. 24. Okay, I give up, but there's lots. So when you are trying to avoid things that you don't have, I mean, the ancient Greeks didn't even have a decimal system, and you're trying to avoid having to work with messy fractions, it's useful if you have a number that you're measuring with, that number can be broken into lots of smaller factors and lots of smaller numbers. So that's why they picked 360 for how many degrees are in a circle. But it is an arbitrary number, and it's not the only way to think about how big an angle is. I'm going to let you do this activity if you want to. I prefer to show this to you with a little animation that I think I just found in Wikipedia. Let's see, can I drag this over? Guys at home, can you see this? I think so, eh? Okay, start over. There we go. If I have a circle with a diameter of 1, look what happens as it rolls. As it rolls, it creates a distance along the ground, and one complete roll is pi. Why would that happen? Okay, we've seen that enough, I think. Let me get it out of here now. Oh, now we gotta back to here. There we go. one complete distance around is pi. Now, why would that happen? Let me kind of show you why that happens. Because remember, you learned back in grade 7 that the circumference of a circle is 2 times pi times r, or if you like, pi times d. So if the d is 1, the circumference is pi times 1. So that little animation I showed you had a circumference equal to pi. Okay, well, we're not going to do that. We're going to use the unit circle. And in the unit circle, the diameter isn't 1, the radius is 1. So on the unit circle, if the radius is 1, then the distance around a circle is 2 pi. So let's see what we can think about that. The formula for the circumference of a circle is 2 pi r. The unit circle has a radius of 1. Therefore, the circumference of the unit circle is 2 times pi. And if you want a decimal, that's 6.28, blah, 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 blah. This means that the distance traveled from the initial arm all the way around a circle is, again, this, which is 2 pi. So if I do a complete revolution of a circle, we call that 360 degrees, but in radians, it's 2 pi radians. If you like a decimal, it's 6.28, yada, yada. A half of a revolution of a circle in degrees is 180, but we would call that pi. Pi radians, or 3.1415926 blah, blah, blah radians. A quarter of a circle, 90 degrees in degrees, a half of a radian. 1/360th of a revolution is 1 degree. We would call that 1 pi over 180 radians, or 0.01 blah, blah, blah. You could actually take your calculator and go pi divided by 180 and you'd get that decimal. So note, the next page here it has note, that 1 radian is 180 divided by pi degrees, or about 57 degrees. So to convert degrees to radians, you take the degree number and you times it by pi divided by 180. And you get the radian number. And whenever possible, we would like to leave our answer as a fraction in terms of pi. The decimals are nice. We can get them. Calculators are real good at spitting out those decimals. You can see that on the right column there. But we prefer, when possible, answers in radians expressed as fractions of pi. So, I should say we prefer. The royal we. All of us. All of us in the brotherhood and sisterhood of mathematics. We're like a cult, really. Us mathematicians. I can think of my career as one long attempt to recruit young people into my cult. Perhaps not the healthiest way to view my career, but it works for me. Okay, so yeah, we would prefer to not have to deal. I mean, look at these decimals. Ooh, what do we call decimals like that? Begins with an I. Irrational, right? Remember, there's no such thing as a fraction that will exactly give you the decimals of pi. How come? Well, it's complicated. But it is true that it's an irrational decimal, like the square root of 2's decimal, or the square root of any non-perfect square. So we tend to like fractional answers better. They're exact. So what exactly is 30 degrees if I wanted to express it in radians? Hang on, let me move over and do that. There we go. Okay, so let's use our little formula. Our formula says take the degree number and times it by 180. Oh, sorry, whoops. I just did this upside down. times it by pi, and divide it by 180. Did I write this down right? Yes, I did. Okay. So, please don't reach for your calculator. On the test, you can't have one. How many 30s go into 180? You can do that. Knock off the zeros. How many 3's go into 18? 6. We call 30 degrees, and we usually say pi by 6, which is a terrible, terrible nickname. Anybody who does carpentry just felt a chill go down their spine, because that's multiply when you're doing carpentry, right? A 2 by 4 is a square that is 2 inches one way by 4 inches the other way. That's the end of the board is a square. It's a rectangle that's 2 by 4. So we usually say pi by 6. Some people would actually say, the British like saying it this way, pi on 6, pi over 6. But yeah, the nickname here in North America, butcherers of other languages that we are, we usually say pi by 6. Okay? What's 225 degrees? Well, we already know it's in the 45 family, and we actually just learned that 45 degrees is, oh, actually we didn't do that, but if we'd have cut this in half again, we'd have got a quarter. Sorry, I forgot where the table ended there. So we have 225 degrees times pi divided by 180. Okay, let's think about this. Again, no calculator, sorry. 5 goes into 225 for sure. Actually, 45 goes into 225. So 45 goes into 225. How do I know that 45 went in? Well, I can see that 5 went in because it ends in a 5. And I know that 9 goes in because 2 plus 2 plus 5 is 9. Remember the trick for 9? If 9 goes into the sum of its digit, it goes into the whole number. So how many 45s go into 225? Well, how many go into 180? Let's count. 45, 90 is 2. So this is 4 45s. And this then would be just one more. 5 45s. So this is 5 pi over 4. Or 5 pi by 4. 720 degrees. Let's think about that. 720 times pi over 180. Oh, hold on a minute. If I count by 180s, I think I hit 720, because 18 goes into 72. So 180, 360, 540, 720. 720 degrees is 4 pi. All right, like everything you've learned how to do in math, you should be able to do it backwards. What if we went the other way? What if we started with a radian number and we multiplied to get it to degrees? Well, we'd multiply by the opposite of what we did the last time. So if I had 2 pi by 3, and I'd like to know how many degrees that is, I times it by 180 over pi. And once again, I'm not letting you use a calculator for that. Pi divided by pi is 1. 3 goes into 180 60 times. 2 times 60 is 120 degrees. Let's go over to C. 5 pi divided by 6 times 180 degrees for every pi radians, right? We're just doing a ratio here. Try to stay with us. Divide, 6 goes into 180 30 times, 5 30s is 150 degrees. Finally, there's something I'll let you use a calculator for. If we give you a straight up decimal that's not expressed in pi's, or the other way around, if we'd have given you an angle up here that wasn't in the 30 degree family or the 45 degree family or the 60 degree family, then yeah, we're going to let you use a calculator. But this one for sure you can do without a calculator, or you need a calculator, I should say. So 1.6, oops, I forgot the decimal. Oops. 1.6 times 180 divided by pi. I'm going to use a calculator. 1.6 times 180 divided by, and every scientific calculator has a pi button somewhere, which isn't a whole lot of help to me looking at this calculator. Oh, there it is, pi. And that's going to be 91 point, I'll just round it to two places, 67 degrees. What if somebody out there was really a traditionalist and said, I don't want decimals. I want an exact number. Well, if it's an exact number, it has to have pi in it. So it's going to be I did it again. It's going to be 1.6 times 180 divided by pi, but we don't want decimals in it. So, we could say 1.6 is 1 3/5. And we could say that 1 3/5 is 8/5. And the reason I say that is because I do know that 5 goes into 180. That's not that hard. How many 5s go into 180? Well, 5 goes into 18 3 times with 3 left over. How many 5s go into 30? Quick, what's 8 times 36? I don't know. Let's see. That's 8 times 36. 8 times 48, carry the 4. 8 times 3 is 24. 288. There we go. It's 288 over pi degrees. That's the exact answer. And again, do you get logically why this is a more exact answer than this? I mean, obviously because I rounded here, but there's no possible way I couldn't round that number because it's never going to repeat. So anyway, I don't think we'd ever ask you to do that, but you've seen it. All right, the easiest formula in grade 12 math is this one. S equals theta r. The central angle is the relationship between the length of the arc and the radius of the circle. So theta is the central angle, but this formula only works when you are in radians. That's why we had to learn radians before we learned this formula. S is what we're going to call the arc length. If you ever wondered how you'd calculate how long a line is if it's a piece of a circle, this is the formula that does it. You need to know radius, and you need to know how to measure angles in radians. So, please note, if there's no unit attached to the angle measure, you assume it's radians. If you don't see a little degree symbol, you just assume it's radians. There is no symbol for radians. Every once in a while you see a textbook use a little r, but most don't. If it's just angle equals number, and there's no degree symbol, nothing, you assume it's the radian measure. All right, let's use this formula. A bicycle tire has a radius of 0.5 and it travels a distance of 1.5 meters. Determine the rotated angle in degrees. Okay, so let's keep track. Let's organize our givens. We know the radius. It's 0.5 meters. We know that the arc length is 1.5 meters. So the bicycle has rotated and gone 1.5 meters. I would like to know theta. So the formula is S equals theta r. Now, I don't know what your kind of preference is for math. I think I like to put the numbers in and then move them around. So I'll put the 1.5 in for S, and I'll put the 0.5 in for R, and then I will divide both sides of the equation by 0.5. So theta is equal to 1.5 divided by 0.5. So theta is equal to 3. And notice that actually doesn't have any units, right? Because I just went meters divided by meters. So the meters canceled. So it is 3 unitless. That means 3 radians of measure. But I'd like to know what that is in degrees. So I take my theta, which is 3 degrees, and I times it by 3 radians, and I times it by 180 degrees per every pi radians. And that's going to be 3 times 180 is 540 over pi. So there's your exact answer in degrees. But if you want a decimal, we punch buttons. Everybody should know where their pi button is. See if you can find it. Take a quick look at your calculator and make sure you know where your pi button is. So 171 point, I'll round it to 2 places, 89 degrees. What's after the, oh, it's an 887, so yeah, 89 degrees. There we go. Okay, so That's one of the other easier things that you might ever see on the provincial exam. In fact, it's almost always question number one. Question number one is usually using the S equals theta R formula. It's a pretty easy formula. You just have to remember, oh yeah, but the angle measurement can't be in degrees until after I'm done using the formula. All right. Coterminal angles. Coterminal angles are angles that share the same terminal arm, such as 70 degrees and its close friend, 430 degrees. Like, for example, I'll use a different color here. Suppose I started here at my 0, and I went around, and then I stopped there. You're probably saying, well, it's 70 degrees. No, it's not. It's the 70 degrees plus the 360 that I went all the way around. That's 430 degrees. What if I started here and I went this way in the negative direction? Well, if I'd have kept going, I'd have had negative 360 degrees if I'd have stopped there, but I stopped before that. So you could think of it as 70 minus 360 degrees, which is negative 290 degrees, right? They're the same terminal arm. They're just expressed as different numbers. Kind of like on a clock, again, a regular clock with a face, you know, like a clock, one of those guys. On a clock, right, 2 a.m. and 2 p.m. are the same place, right? They're the same place on the clock. Same idea here exactly. This terminal arm would be the same terminal arm for 70 degrees or 300 or 430 degrees or negative 290 degrees. Let's try a couple of examples. Oh, a little bit of notes first. The coterminal arm can be found by adding or subtracting revolutions. If you're in degrees, you plus or minus 360. If you're in radians, you plus or minus 2 pi, because remember, all the way around is 2 pi in radians. And yes, there's an infinite number of coterminal angles. Give me 3 coterminal angles for 40 degrees. Well, okay, how about, so 40 degrees is, say, about there. So there's 40 degrees. How much would this one be? And then what if we started and went this way? How much would that one be? So let's say, so 40 plus 360. This guy here was 400 degrees. What about the one where I went around the other way? This guy here was 40 minus 360 is negative 320 degrees. And then for a third one, spin around again. How about for this one, we start here, and we go around, and around again. There. How much is that guy? Well, that'd be 40 plus 360 doubled, which would be 720 plus 40, 760 degrees. You got to be careful when you try to draw those. You can kind of get lost in your own spiral trying to draw those. Uzumaki. I believe that's Japanese for spiral because there's a really cool manga called that. I like scary mangas. The superhero ones are okay. Japanese versions of Marvel and DC superheroes they're okay. They're fun. But it's the horror stuff I totally dig. All right, let's do this not in degrees now. You ready? Where is pi by 6? Now, I know I just introduced this a few minutes ago. A few minutes ago, you were young and innocent, and all you knew is that angles were in degrees and the world was good. Well, I'm afraid we can talk about angles as being in radians too. And if the first thing you want to do right now is convert that to degrees so that you can kind of figure out where it is, well, you're new to this, so I'll allow it. How many of you here, I'd imagine I'm the minority in this room in that I only speak one language, right? I grew up speaking English. When it comes to French, I could sort of understand my grandma, and I can order food and take directions when I'm driving around in Quebec. That's about the best I can do. I am not bilingual, and I'm not fluent in any other language. Those of you who are bilingual, you know that once you are learning a new language, you aren't really mastering it until you're thinking in that language. You are not really speaking English if every word you are doing in your head is a translation. You actually have to think in English to speak English. And that's kind of the way I want you to go with radians. Try to count in radians. What does this, if you remember that this is pi, where's a sixth of pi? Out there? 1 6, 2 6, 3 6, 4 6, 5 6, 6 sixths. Same place, right? Okay, again, if you really wanted to, it's 30 degrees. But good enough. Pi by 6 is about there. So give me 3 coterminal angles for pi by 6. So here's one of them. So all angles are coterminal to themselves. And then how about we go all the way around once? What would that be? It'd be pi by 6 plus 2 pi, which I am going to change into pi by 6 plus 6 pi. No, I'm not going to do that. Plus 12 pi by 6. And I'm going to say then that this one that I just drew here is 13 pi by 6. Let's do another one. Let's go the other way. Let's start here and go that way. So that one would be pi by 6 minus 2 pi, because I'm spinning around in the opposite direction, which is pi by 6 minus 12 pi by 6, which is negative 11 pi by 6. So that's what the blue one is. And let's do a big one, a big spiral. Here, I'll just kind of dot it really lightly. We start here, and we pass it once. We pass it twice. And then we stop. Uzumaki. So that would be pi by 6 plus, you could either just say 2 times 2 pi, or you could just know that spinning around twice is 4 pi, and spinning around 3 times it'd be 6 pi, and spinning around 4 times it'd be 8 pi, etc., etc. So that's going to be pi by 6 plus, now how does 4 pi end up being over 6? You just times 4 by 6 and get 24. So 25 pi by 6. And there we go. So there's the B one. All right, for C, find me a coterminal angle to 740 degrees. Over the interval from theta is less than 0, but more than negative 360 degrees. So in other words, starting here and going around this way, there we go, that's negative 360. Find me something that's the same as 740. So start at 740, and remember that if I'm going this way, I'm going in the negative angle direction. Every time I spin around, I'm taking away 360 degrees. So that would be 380 degrees. Okay, except, well, that's not in my interval yet. That's still positive. So let's keep going. Take away another 360. Well, no, that's still not going to work. 20 degrees, that's still going this way. So one more time. Negative 340 degrees, that one works. That's my answer, right? Between 0 and negative 360, if I go to negative 340, I hit that same place that would have been 20 degrees or would have been 380 degrees, but it's within the interval I'm looking for. So that's how I do a question like C. Look at D. Determine all the coterminal angles of 5 pi by 3 if I'm going. Now remember, this is interval notation. So I'm saying that I have an angle that goes all the way to negative 4 pi or to 2 pi. So that's, I might as well do that kind of in 2 diagrams. Negative 4 pi. So starting here, going around once there, that's negative 2 pi. And then going around again there, that's negative 4 pi. That's negative 4 pi. And so that's this one. This guy, looks like I drew a snail. This guy here would be starting here and going in the positive direction. So there's 2 pi, right? Remember, positive is going counterclockwise and negative is going clockwise. Okay, so determine all the coterminal angles. So let's see. There's going to be a lot of them. How many places? First of all, where is 5 pi by 3? Well, if you're counting by thirds, one more third and you'd hit 6 pi by 3, which is 2 pi. So that's actually, say, here. 1/3 of the way that way. This is 5 pi by 3. How many times do you hit this line in these two diagrams? Well, let's try 5 pi by 3 plus another 2 pi. Let's see. Well, that would actually give me 5 pi by 3 plus, let's see, if we count in thirds, how much is 2 wholes? 6/3? So that'd be 11 pi by 3. Oh, wait a minute. 11 pi by 3 is too big. I have to stop at 2 pi. So too big. So all of my answers are going to be minuses. So 5 pi by 3 minus 2 pi's, which again mathematically is 5 pi by 3 minus 6 pi by 3. So there's one answer. That one would be in the spiral going around once. But what if we go around again? Let's minus another 6 pi by 3. So let's see. Pi by 3 minus 6 pi by 3 is negative 7 pi by 3. Is this still in the interval? Maybe I should take a second and count this in thirds. How many thirds is 4? 12. So there we go. Is 7 less than 12? Yes. This is an answer. Will I get another answer? No. Because if I were to take, here, I'll do the math here and show you. If I were to take negative 7 pi by 3 and minus 6 more, I'm going to get negative 13, which is too small. So my answer is, there's two answers. They're both negative. And there we go. Now, what the heck does this mean? Express a general form for all coterminal angles, not just the ones between here and here, but all coterminal angles. What can you say about them? Well, you can say that an angle that's coterminal to 5 pi by 3 is equal to 5 pi by 3 plus or minus 2 pi n, where n, fancy mathese coming at you here, is an element of the natural numbers. In other words, n is 1, 2, 3, 4, 5, or 6. Okay? And I guess that does kind of counteract what I said earlier, because I said all angles are coterminal to themselves. I guess mathematically that's not true. You wouldn't say you're coterminal to yourself, or else this would be a W, not an N, because then you'd count 0. But I'm very sure in the notes it says don't use W, use N. Oh, it even says right here, yes. Okay, I'm going to write it down. N, with the extra line, is the set of natural numbers where 0 is not included. So it's 1, 2, 3, 4 to infinity. And we would say 5 by 3 is not coterminal to 5 pi by 3. It is 5 pi by 3. So there we go. And that's lesson 1. I know, that's a long lesson. Okay, let's see. And